Thank you for your introduction. My name is rather difficult to pronounce. It's named Chiaki Uyeda.
Chiaki.
Uyeda. And you can see from my affiliation, I'm far from material science. I work at the Institute of Earth and Space Science. But I've been working for some days on to measure magnetization of small diamagnetic materials for some time, and I hope my report may provide some information to material science. Now, my contents are as follows. The first half is about diamagnetic susceptibility measured by from magnetic translation. The second is the diamagnetic anisotropy measured by magnetic oscillation. The two parameters are basic parameters to know the magnetic property of a material. And first, I start with translation. We prepare our monotonically decreasing field in microgravity condition, and we quietly release a diamagnet particle in the magnetic gradient, and the particle will translate by repulsive magnetic force towards the zero magnetic field. And we found that the terminal velocity outside the field is independent to mass. This happens because when you consider the energy conservation rule, the particle M appears on both sides, and this is deleted. So we can measure a very small particle, no matter how small it is, by measuring the terminal velocity. And another thing that we found is that if we release a bunch of group of different heterogeneous materials at the same place, it will be divided, separated into groups of different materials when they reach the outside the field. And in order to confirm this, we performed experiment in microgravity condition. This is a cut view of the setup that works. Oh, sorry. It worked. Cut view of this system, and magnetic field was generated by two magnetic plates, and field of magnetic field is in the vertical direction, and it monotonically decreases in the x direction. And sample is set right here. It is at the edge of the gap. This is where the magnetic force becomes the maximum. And diamagnetic materials will be translated outside the magnetic field and will be collected on the plate here. And I'm going to show you a movie. This is, we set three types of diamagnetic materials: graphite, bismuth, and diamond. And graphite has the largest absolute value of diamagnetic susceptibility, whereas diamond is, the chi value of diamond is almost 10 times smaller. Note that these two materials are both composed of carbon, single carbon. So you can divide these two materials by magnetic field. And this is, I'm going to show you the movie. We have three pieces of graphite. It moves away in bismuth and diamond. So you can divide all sorts of materials by the simple setup. The magnetic field is only 0.86 Tesla. It's made by a permanent magnet. And we collected, this is a picture of the magnet plate, collection plate, taken after the experiment. And you can see that the graphite is at the left end of the collection plate. And all the other materials have an absolute value that is smaller than the graphite. So all the other materials, even that are not set here, will be collected in this very small area. So it may be like, this may be like a kind of a optical prism. You can divide all sorts of materials with a permanent magnet, a simple permanent magnet in microgravity condition. And we also measure the magnetic susceptibility chi value from the terminal velocity, and the measured value is in good agreement with the published value. And all the materials is expected to distribute between graphite and diamond. So from this graph, we can see that the energy conservation rule, as we assumed here, is effective on all materials in general. And another thing that we have a list of published values for all materials. So by collating the chi value with the list of these values, we can identify the materials, even if the material is not identified. And so much for magnetic translation, and we move on to magnetic alignment. And we know that anisotropy of delta chi, we can, by the anisotropy of delta chi, we can we see that a diamagnetic material can exhibit rotation by a field-induced anisotropy energy. And we know that attempts have been made to produce functional materials by aligning the microcrystal in one direction, like this. But and according to the classical Langevin model, the alignment occurs when the field-induced anisotropy energy is larger than the Brownian motion energy. So the magnetic field required to cause alignment is determined by three parameters: temperature of the system medium, and mass of particle, and the delta chi value. So the delta chi value is very important in designing a process to produce a functional material. So we want to measure the delta chi value of diamagnetic materials, but actually it is basically very small. And in a conventional method, of measuring delta chi, we suspend the sample, single crystal, with a rigid fiber, and apply a magnetic field, and the stable axis will tend to rotate towards the magnetic field, but then it balances with the restoration torque of the fiber. And when you have to measure a very small delta chi or very small sample, the magnetic torque is very small, so this doesn't work. So we considered another system. We simply deleted the fiber from the system and actually released the sample in an area of homogeneous field using microgravity. Then the stable axis showed rotational oscillation with respect to the direction of field. And we have a equation of rotational oscillation here. And the delta chi value is obtained for the period of harmonic oscillation. The stable axis shows oscillation with respect to the field, and the chi value can be measured from the determined from the period of harmonic oscillation. Note that we don't have to measure the M value, mass value, because mass values appears in the inertia. So again, you don't have to measure the mass, and you can measure a small microcrystal so long as the oscillation is measured. And using this system, we were able to compile many materials, inorganic materials and inorganic materials and organic materials. And some of them were newly obtained, and for other materials, we were able to correct the published values that were measured many years ago. And for each material, we calculated the field intensity to achieve full orientation of micro-sized materials. You can see that these values are in Teslas, and for most of the materials, you don't have to use a superconducting magnet. You can align the particles by an ordinary electromagnet or even a permanent magnet. And for carbonaceous materials, we can see here that we know that graphite has a very large value. It can be easily aligned by magnetic field. We also know the value of carbon nanotube. It was measured about 20 years ago. So for these materials, we can align the materials and make a functional material. But for diamond and amorphous, they're supposed to be isotropic, and it's supposed to have no delta chi. But my personal expectation is that this may not hold true in nanoscale, because the crystal structure may deform. And next, I'll show you an example of detecting a small delta chi from a small sample piece. Here, we wanted to prove that amorphous silica, it's supposed to be isotropic, may exhibit a large anisotropy to cause magnetic alignment. Now, one possibility is when the molten silica is cooled rapidly, a large temperature gradient will be located in the direction normal to the surface. It's about 1,000 degrees per centimeter or so. And some kind of anisotropy may arise in the local atomic arrangement in the surface area. So we synthesized the amorphous silica. It was heated to about molten at about 1,250 degrees and cooled at about 0.5 Kelvin per second. And next, I'll show you the example of an experiment performed in microgravity. A sheet sample, this was released from the surface of the molten silica. It was set on an inclined plane on a sample stage. And this plane is always parallel to the surface plane. And static magnetic field was applied. It was about 0.52 Teslas. Now I can show you you see that the small glass plate rotates, rotational oscillation for about several strokes. And you can measure the delta chi value of a small sample from the period of harmonic oscillation. And this is the depth profile of the chi value obtained from the surface of the molten silica. And you can see that there is a very abnormally large delta chi value at the surface. This value is comparable to the value of an ordinary mineral, silicate mineral in nature. And the EC plane was always parallel to the plane. It was the normal plane of the surface was the unstable plane. And it gradually, rapidly decreases, but still we can find some delta chi left in the interior. I think it is very interesting. So we tried this experiment again and again, changing conditions, and we got a good reproducibility. So I think this is not a fake. Now, maybe this is a small small summary. Magnetic property has been conventionally characterized by two parameters, namely chi, susceptibility chi, and its anisotropy delta chi. And in terrestrial gravities, the influence of signal from the sample holder are not negligible in both measurements, especially for small samples. So therefore, magnetization of solid particles below submillimeter size it's very difficult. And presently, in these samples, you make a grain aggregate sample, which secures the sample mass that is required for the measurement. So in this sense, the two methods performed in microgravity that I show you may be a hint to detect magnetization of a very small and single nano-sized particle in the future. Now for a conclusion, so delta chi, the chi value of a solid particle is swiftly obtained from its field-induced translation realized during a short microgravity condition. The delta chi value of a small single crystal is obtained from its field-induced oscillation in microgravity area. And using this setup, a large anisotropy was detected at the surface of a quenched amorphous silica. So I think this may happen in other types of amorphous materials, such as carbonaceous materials. And third, the magnetization of a small single particle is obtained from the observation of method 1 and 2, no matter how small the particle may be. This is possible because the magnetic volume force that induces these motions are proportional to the mass of the particle. And fourth, finally, this is my personal expectation, but the extent of structural transformation in a nano-sized particle from the bulk crystal may be estimated from its magnetization. This is because the values of chi and delta chi originate from the spatial distribution of localized electron in the intervisual particle. Okay, that is all. Thank you for your attention.